Okay, thank you for the introduction. So it's really an honor to be here with you today to present our talk, SVF, Static Value Flow Analysis in LLVM. So first of all, I would like to thank LLVM committee and the CC committee to give me this opportunity for a plenary talk. And this is especially for a junior researcher like me. So this is a joint talk, joint work with Peng, Ding, Hua, and Jinling. So this talk is not about a paper or a novel idea, but rather we would like to share some of our past experience on static value flow analysis and the point alias analysis and the tool we have developed during the past few years. So this is the outline of this talk. So first, I'm going to introduce static value flow analysis and the motivation of this work. Next, I'm going to go through the design overview of SVF, and then we look closer to the internal working of SVF with a single example in the form of LLVM IR. So finally, we will give some experimental results and planned applications based on SVF. So static value flow analysis resolves both control and the data dependence of a program. So it generally answers the questions, for example, from bug detection to like, does the information generated at program point A flow to another program point B along some execution path? Or is there any unsafe memory access that may trigger a bug or a security risk? So following the LLVM IR, we separate variables of a program into two categories. So the first category is top-level pointers or register value. So their depth use or value flow information are explicitly on the LLVM SSA. So the second category, we call it addressing variables or allocated memory. They can only be indirectly accessed using top-level pointers at load or store, which requires pointer alias analysis. So the depth use of addressing variables are hard to compute precisely and efficiently, especially for real-world large-size programs. So let's take a look at this picture, which shows a relatively small program from spec to SVF benchmarks. So we can say each rectangle represents a procedure. And inside the rectangle, we say this is a control flow graph, and each node represents a basic block, and each between them represents a control flow relation. So we can see it's really costly to reason about flow of values on CFDs. So for this larger program, it does not have only complex control flow, but also have very complex calling relations between different methods. So this is a call graph of DCC. We break down into several strongly connected components. So each rectangle inside is a strongly connected component. So we can say this picture shows a very complex, strongly component involves hundreds of methods. So let us enlarge this picture. We can say it's really a mess here. So there's a lot of calling relations between different methods. So it's clearly it's very costly to reason about flows of values across different procedures interprocedurally. So the static value flow analysis and pointer alias analysis techniques long-standing research. So during the past decades, there are many research ideas on the algorithm have been proposed. So one motivation of this, especially the recent progress in sparse analysis, which shows a promising solution for analyzing large-size programs. So one motivation of this work is to bridge the gap between the recent research progress in point alias analysis and the existing engineering efforts in LLVM. So we know there's lots of point analysis variations like flow sensitivity, context sensitivity, path sensitivity. So implementing or re-implementing an existing point analysis algorithm is painful, right? So there's many reasons behind. The first is the difficulty of the aliasing problem itself, and also there's a lot of complex engineering details often ignored in a research paper, and many implementations on different platforms, and some of them are quite densely coupled, which is difficult to reuse. So it's time for us to rethink how could we develop reusable and extendable and also robust analysis framework that uses layers of abstractions so we can minimize efforts of implementing a sophisticated analysis. So with the hope that we can also enable more interesting research in this important field. Like we can sort of write few hundreds of lines code for a single analysis instead using thousands of lines code, right? So another motivation of this work is many client applications require precise interprocedural value flow analysis, especially for some static bug detection tools like memory leak detection, user after-free detection, and data risk detection. All this requires like scalable, precise program dependence analysis. So another application is SAN headers, right? So we know that SAN headers have been used worldwide. It's already become an essential part for software testing. So it's also because it's also like we can use some precise program dependence analysis to remove some of the redundant instrumentations. So any performance improvement can be beneficial, right? So next is, of course, the program understanding, because static value flow analysis can similar like program slicing tools, so we can help users to understand the dependence between different statements. So the last motivation is definitely the LLVM community, because LLVM is established compiler with well-defined IR. So there's many front ends. So there's a possibility we can write analysis to analyze many other programming languages, right? And of course, they have a very supportive, friendly community. So many active program analysis researchers and also engineers here. So with the above motivation, we have developed a tool called SVF, that supports refinement-based interprocedural program dependence analysis on top of LLVM. So basically, there are two major components, point analysis and value flow construction. So they are performed iteratively to provide increasingly improved precision for both. So the project initially started from 2013 on LLVM 3.3. And the noise supports LLVM 3.7, so we are still working to try to catch up with the latest release version of LLVM. And also the source code is public available and hosted on GitHub site. And let's go through each of the major components to see the design overview here. So unlike many of previous point alias analysis, their implementation are quite densely coupled. So we simplified point analysis using three loosely connected components, namely graph, rules, and solver. So the graph is a higher level abstraction from the LLVM IR, so indicating where the point analysis should be performed. And rules defines how to derive the points information from each statement. And the solver defines in what order those constraints or statements should be processed. So with this loosely connected component, we can easily assemble a point analysis by using different combinations, right? So for example, a simple flow incentive Anderson analysis can be performed using the transitive closure rules on top of a constraint graph, and with constraint solver techniques like wave deep propagation and or lazy cycle detection. So similarly, flow sensitive analysis can be performed on a depth use graph or value flow graph with a SCC topological solver using iterative data flow analysis. So also, different point analysis techniques can choose different points data structures. For example, context-insensitive analysis, we can use the plain bit vector data structure to represent pointer and the memory object. And context-sensitive analysis, we can use the conditional map to instantiate different qualifiers before the pointer and the memory object, like context calling program calling context and program pass information to eventually implement context-sensitive or path-sensitive point analysis. So given arbitrary point alias analysis produced, the points information can be used later to annotate the side effects on the program statement, and then we can eventually build the memory access form and generate a value flow graph. So before we build the memory access form, we want to partition the memory object into regions so that we can reduce the overall construction time. So the most conservative one for the memory partition is that we treat all the memory object like a single memory region. In this case, when you modify an object, it means other object will be affected. So the most fine-grained way is to treat each memory object as a single memory region. So in this case, it's not that cost-effective. So the better way would be we partition the memory object into objects into memory regions that are accessed equivalently. So given the memory region we have partitioned, so next step is we need to construct memory accessible form. So we follow the HSA, which has been proposed in a very long time, CC paper. So this algorithm or this HSA form has been implemented in OpenSix4, and it shows effectiveness for many years, although OpenSix4 has already died now. And these two major steps for the construction. The first is the side effect annotation, which essentially use the pointer information to annotate at the memory access statement and the call set to indicate their modification side effects. And the next step is to place the memory access file node at the conjunction point of a control flow. And finally, we will perform the access renaming to rename all these memory object or memory regions. So given the memory access form, eventually we will see that the built-in depth use chance has already been set up. So basically, you can connect the direct value flows, which means the defined use of top-level pointers, which already exist on the LLVM's SSA form. And then we also connect the defined use of address-taken variables we have built using the SSA form. So given the value flow graph, so we can either feedback the value flow information into the pointer analysis module to use this use this representation to perform more advanced pointer alias analysis, like context-sensitive, flow-sensitive, path-sensitive, or we can use this value flow information as a foundation for many static analysis, or use this information to accelerate dynamic program analysis. So the following papers, which has been done in the past few years in our group, so basically focusing on using this information to detect memory leaks and accelerating dynamic program analysis, especially the sanitizers. So let's look closer to the internal working of SVF using a single example in the form of LLVM IR, so we can understand more how it works, go through the three main paths, which namely point analysis, interprocedural memory access form, and the value flow construction. And finally, we see how to extend SVF to support multi-threaded programs. So let's start with a very basic point analysis, Anderson's point analysis. So SVF transforms LLVM instruction into a graph representation we call constraint graph. So each node on the graph represents either a pointer, the pointer value in the LLVM value in pointer type, or a memory object, which is either a heap location, stack location, or global variable or function object. So each edge between two nodes represents the constraints. So we translate all the instruction into 5 basic constraints, namely address, copy, loss, store, and field access. So eventually we will using the transitive closure rules to resolve those constraints and generate the final points to relation. So let's take a concrete example, right? So we have this simple example, which is a swap example with a body here. And we have 2 pointers, A and B, which point to two stack variables, A1, and the second field of a struct object or aggregate object. So after the swapping, we know that A and B the value of A and B will be swapped. So we compile the program into LLVM representation using clone and with memory to register option turned on. So we can say this 4 allocation instruction is basically allocate 4 memory stack on memory object and assign them to 4 pointers, A, B, A1, and ST. And these 2 store statements correspond to these 2 assignments, and this get element pointer instruction corresponds to this field access. So this is a body which has been compiled into LLVM representation with 4 instructions. So we first translate the LLVM instruction per function. So we build a sub-constraint graph for each method. And we use these colors to reference different kinds of constraints. So for the first 4 instructions, the allocation instructions, we translate them into address constraints. So each node with a double circle represents object, and each node with a single circle represents the pointer. So at the right corner of a pointer, each reference is point to site. So we will also translate to the statement and the instructions into other kinds of constraints like store and field access, and also the constraints from the body of the swap instruction, a swap body. And also we connect the inter constraints of different sub-constraint graph according to parameter parsing. And then we perform the constraint resolution to solve this graph, and eventually until a fixed point. So there's many constraint resolution techniques we have mentioned, like several constraint solvers have been proposed by other researchers. So more details can be found on the wiki site of our tool. So the next step, given the points to information, we would like to annotate the set effects on the LLVM IR. So basically, the memory SSA form is constructed per procedure given the global points to information after the partitioning. So the first step is we perform the set effect annotation. For each load instruction, we annotate with a mu function to indicate the read set effect of an object, memory object O. And a store statement indicates the indirect modification set effect at a store of memory object O. So the call set is similar. For each call set, we also annotate with mu and chi operator to indicate there's potentially the set effect modification of the memory object O inside the callee function. And the function parameter, function entry exit also annotated with mu chi to indicate that if a memory object O is not defined in the current scope, so it may be modified or maybe indirect read inside the current function scope. And the next step is to construct memory S form by placing the memory SSA file for the memory agents or memory object. And next is to renaming. So we treat the mu operator as a use of the memory object, and treat the chi operator as both the define and the use of a memory object. So let's take a look at how it looks after translating the previous example, LLVM IR, and annotate all the study facts and build the memory SCC. So it looks like this. So let's take step by step. First, we annotate a study effect with mu, which highlight use blue color, with chi with highlight with blue color. And next, we annotate mu with annotate the load instruction with mu operator. So here we just simply treat each object as their single memory region, right? So next we annotate the call set with mu and chi, and eventually the function tree and exit. So finally we get the annotated memory SVF form on the LLVM IR. So the next step is basically to construct a value flow given this memory SVF form. So on the value flow graph, each node represents a definition of a variable, and the edge between two nodes represents the def-use relation of a variable. So we can see the top-level pointers are easily connected, and their def-use relations are easy to be represented. Right? So the thing is, we also leverage the annotated side effect information in the LSSM form, so we connect the interprocedural value flow for the adjusted variables, which is O1. Similarly, so O2, and then eventually we connect. We leverage all the side effect information to connect the whole program or interprocedural value flow information. So eventually it will be look like this. So after the value flow graph has been constructed, the thing is the client application may ask, what's a points value after the function swap being called? So we know that this point B after the swapping will only point to the object A1 instead of the field object as T.F2. So how do we do this? We just simply add a dummy loss statement to trigger this query, and then we trace backwards against the value flow to answer these queries. So interestingly, when we arrive at this store node, there's two choices tracing backward. One is follow the value flow from the previous value. Another option is to trace back from the right-hand side of the store statement. So to decide which way to go, we employ a notion called strong updates, which means if the pointer operand of a store statement only points to a single memory object, which means the old value flows to the store statement will be killed. So we only move backwards from the right-hand side of the store statement. Eventually, we will reach this allocation assigned to the pointer A1. So we know that this pointer B only points to the object A1. So we know roughly how to perform the point analysis, construct memory SCC, and eventually generate the value flow graph. So next, we will see how to extend the SVF to support multi-threaded program. So the thing is, we have a thread line code which use the previous phase to generate define use for these three statements. All the dereference here assume accessing the same memory object A. So if we replace the first statements with a fork side, and then eventually we will have this code, and we put the first statement into the function, results in the second thread, right? So we will have interestingly, because in multi-threaded program, thread interleaves, we need to figure out the inter-thread value flows. So for one scenario here, if we assume the first scenario is S1 execute before S2 and S3. In this case, the value flow will be kept the same. So essentially, the fork side is treated like a function call, right? So for the other scenario, like S1 is execute between S2 and S3, in this case, the value flow will look like this. So the third case is S1 executed after S2 and S3, so there is no outgoing value flows from S1 to S2 and S3 because S1 is executed after them, right? So the case becomes more complex when considering other synchronization primitives. For example, the fork side and the lock-on-lock. For example, in figure 1, if we place a fork side immediately after the join side, so we will say there is no thread interference between S1 and S2 and S3. Similarly, S1 cannot execute between S2 and S3 if they are protected by the same common lock. So how do we solve this? We, in order to obtain sound and precise inter-thread value flows, we perform a series of static, context-sensitive thread interference analysis to reason about fork join, memory access, and lock-on-lock. Eventually produce thread-aware value flows to combine with the previous value flow we compute so that we can generate sound and precise value flow for both single and multi-threaded programs. So the details of the algorithm, please refer to the paper we have published this year. The next we will talk about the results, the experimental results, and the client applications on top of SVF. So we try to evaluate SVF using as many benchmarks as possible. So we choose all the spec benchmarks, including 15 programs from spec 2000 and 12 programs from spec 2006. And also, we evaluate SVF using 20 open source applications. So all these applications across different domains, including scientific application, server application, and multimedia application. And most of them are recently released. So the total length of code evaluated is around 8 million lines of code with a maximum size of the code more than 2.5 million lines of code. So we use the Go plugin to eventually combine multiple files into one so that we can analyze the program interprocedurally, basically the whole program analysis, with the machine set up as here. So this graph shows the analysis time of benchmarks we have evaluated. So the total analysis time includes Anderson analysis time, memory SSA, and the value flow construction. So in the x-axis, it shows the name of the 35 benchmarks we have used. And the blue bar or the green bar here shows the analysis time in seconds. So the green dots here shows the code size of each benchmark. So we can see generally when the size of a program grows, the analysis time increases. So we can say there are a few exceptions. For example, this one, PSAN, this benchmark, actually its analysis time is higher than the third one, GoScript. However, the code size of GoScript is larger than PSAN. The reason is because PSAN, this program is more complex. It has this number of pointers in PSAN has more than twice than that in the program GoScript. And we can also partition the program into several categories. For the program up to 200,000 lines code, we can analyze all this code in seconds. So up to program to 500,000 lines of code, it usually takes 10 or 20 minutes to analyze them to generate the whole program value flow. So for the largest benchmark, especially the GDB and PSAN, it takes hours to eventually generate the value flow graph. It's around 4 hours for the generate the largest one. So this graph shows the analysis time distribution. So generally we can see the pointer alias analysis takes the largest portion of the total analysis time, and it's around 72%. And the value flow graph comes next. It takes around 17%. And also the memory SVF comes last. It takes 11%. So this graph shows the flow sensitive point analysis slowdown against the flow insensitive Anderson's analysis. We can see generally the slowdown the range from 1.2 to 44 times. And on average, it's roughly take 6.5 times slowdown than flow insensitive one. So let's take a look at several client applications on top of SVF. So one important application, I think, is to detect source sync related program bugs, especially the memory leak. So this work has been done in 2014 and 2012. So the basic approach for detecting memory leaks is every object created at a location site, we call the source, must eventually reach one free site during any program execution pass. So the nice thing about SVF is that it provides graph representation, sparse graph representation that captures both the defined use of top-level pointers and addressing variables. So we can solve this problem using a graph reachability in a demand-driven manner. So it usually provides more trade-offs between precision and efficiency compared with other detectors. So the next important application is sanitizers, especially memory sanitizers. So we know that in C, global variables are defaultly initialized, but heap and local variables are not. So the memory sanitizer detects uninitialized memory access by source level instrumentation of LLVM IR. So the basic idea of this work, which is done in 2014, is to identify the safe memory access according to the value flow information. So we say memory access or checkpoint is safe if there is no value flows reachable from undefined location. So if there's at least one, we just keep this check. So basically, there is 4 settings for this work. The first setting is we just only trace the direct value flows. Essentially, we don't need SVF, right? So the next setting is we trace both top and the drastic variables to identify the redundant check. So the third and the fourth setting basically optimization. So the third setting, which means to try to reduce the shadow propagation. For example, there's thread line code X to Y to Z. If the shadow is not used in the instrument Y, so all these value flows are same variables. They eventually will reach from X to Z, then we can reduce the shadow propagation from X to Z. So the third optimization basically is the redundant check optimization. So for example, if the check say is redundant if all value flows to say it has been checked already. So it's like a double checking for pointer dereference along the control flow. So this graph shows improvement for the overhead generated by memory sanitizer. So the x-axis shows the name of the benchmark. The y-axis shows the execution time slowdown, normalized with respect to the native run. So the black bar shows the memory sanitizer's overhead is generally like 3 times slower than the native run. So we can say the second setting contributes most to the performance improvement. So it shows the effect that we need to analyze addressing variables as well. So this work is based on the insight is that most parts of the program is safe, which means most of the variables has been initialized. Only parts of the program need to be checked and identified at runtime. So another application is to accelerate thread synthesizers. According to our previous slides, also we have a inter-thread value flow. So the thread synthesizer basically finds a thread find the memory access conflict during the thread interleaving at runtime. So it's also instrument the memory access to check them dynamically. So if a runtime check for memory access is redundant if it has no outgoing or incoming thread inter-thread value flows, which means because the inter-thread value flow is our approximation. So if there is no incoming outgoing, it means at this memory access, it is thread interference free. So we can safely remove this check. And the underlying techniques is we use the pointer information to identify thread local memory access, and with the MHP or mayhappen parallel analysis, alias analysis, and the log analysis to remove redundant checks. So this graph shows roughly the speed up compared with the original TSAN. It's roughly around 2.3 times faster than the original TSAN. So this work has been published in PMM, so the details can be seen in this paper. Okay, yeah, I think I got to come to the conclusion session. So we have a present research tool which supports refinement-based inter-procedure program dependence analysis on top of LLVM, and it supports developing different kinds of point analysis algorithms, and it supports inter-procedure memory SAC form and the value flow construction. So the future work, I believe there's many interesting things can be done there. So there basically, I think, is two interesting directions. So the first one is to leverage SVF to enable more advanced analysis. Especially we want to support SVF for C++ and Objective-C, so we can add more new features or advanced analysis, like object sensitivity analysis, so we can make the core graph more precise. The next interesting direction is we are developing is that we want to try to use SVF to perform more advanced demand-driven flow context and heap-sensitive analysis. So, previous demand-driven analysis or using the CFL reachability or performed on the graph without the program control flow information. So, based on the new representation, namely the SVF, we can enable more advanced demand-driven analysis by using the graph reachability. We can refine those superior value flows. So another interesting direction is for the bug detection. I believe there's many more bug detection tools can leverage SVF, especially for like user-free, which is also very critical bugs. And without precise static analysis, I believe there will be many more false alarms there. And also, it can enable more advanced alias analysis to enforce control flow integrity, which is also a very hot topic for recently for security reason. The next thing is interesting is because nowadays web of fuzzing or dynamic symbolic execution is very it's very effective for software testing. So we are not only trying to accelerate dynamic programs only, but we also it's also interesting to investigate how to accelerate dynamic symbolic execution to generate more meaningful test cases. Yeah, I think that's it. Okay, thanks.
It's question time, so if you...
Hello, Weiren Huang from Huawei, and can you go back to the slide that show the experiment environment set up?
Do you mean
Yes.
here?
I know that the machine has huge memory. Does your analysis need such
Yeah,
memory?
yeah. I think that this is a good question because for the inter-procedure analysis, it's not only takes more time, but also more memory because you are analyzing the whole program. So for the benchmarks we have evaluated, actually some of the benchmark, especially for the largest one, it takes, if I remember correctly, it's like 20 to 30 gigabyte. Because the bitcode size itself is quite large. It's more than hundreds of megabytes, or some of them is nearly 1 gigabyte. So it's really essential. We have to perform some of the analysis, especially for large program on the machine with huge memory. Yeah.
Thank you.
Hi, Eyal Zaks from Intel. So 2 questions about mitigating the amount of time it takes. One is you can use this for optimizations and transformations. So have you given thought as to invalidation and how you can adapt the information that you've gathered once you've done some transformation instead of having to run this over again? And the other related question is, can this be demand-driven so that if I want to ask only about some pairs of pointers, can I save something by computing only what I'm asking for and not having to run the whole preparatory stage?
Okay, I think for the first question, actually we pay a lot of efforts on the optimization of the analysis itself. For example, for the most expensive part, especially the point analysis, we are trying to leverage the existing constant resolution techniques to write a more efficient solver, and also we try to do some caching techniques, which essentially to reduce the propagation for the points to information. And also the SSA is another memory SSA. Another technique is that we try to partition the memory that we can minimize the effort when constructing the memory SSA. Because inter-memory SSA, inter-procedural memory SSA, the basic meaning is that we try to record, or we try to identify the memory access globally. But we construct the memory as form parameterized. So basically, for each memory as form, we not only construct the whole memory as form across the whole program, but we construct the memory as form according to the global information per procedure. So this is also the optimization there. For the compiler side, which you have said can we use some compiler optimization to reduce the code size itself, so we can also reduce analysis overhead. Yeah, I think it's also an option that can immediately be done. But we try to keep the original information on the of the bit code, so we can not only do the optimization, but also we can try to use SVF to do the bug detection. And for your second question, how do we use the pointers? So it's basically the demand-driven, if I understand it right. So the thing is demand-driven. So we can start demand-driven analysis in various ways. So the simple way is we just give the representation instead of constructing all this sort of dependence stuff. In this case, I think they can perform the demand-driven in a imprecise way, because with the less information you obtain, you definitely have to try to refine it later. So it also takes it's a trade-off, right? So it may take efforts when later on you try to refine it. But if we start with like a more precise representation, we can further perform more advanced analysis. I think it's also a good way. And also we are trying to also scalable to very huge programs, so people can perform all this sort of sophisticated analysis on a more advanced representation. I think it's the efforts. I think it's worth to pay. Yeah.
Yeah, we use the demand-driven approach in the SNC compiler for the PlayStation, for example. It was quite effective. We also had problems that often you couldn't resolve which, the origins of a pointer until you resolve the memory dependencies themselves. So often there were many sort of layers of resolving memory dependencies before you could work out exactly what the pointer was, the set of things that the pointer could point to. But I'm going to ask you a question on the C++ side of things, because C++ is very different from these sort of quite venerable old pieces of C code, which we've been testing with. In particular, good modern C++ doesn't have any global variables at all, and everything's done through fields in classes. So I guess you've got some ideas about that.
Okay, so about C++. So for C, we also have aggregate structures like struct and nested struct as well. So based on our experience, so in C, also we have a very huge structure, especially for structs especially for large programs. So not only like tens of hundreds fields of a struct. If we consider the nested structure, it may have thousands of the fields of a struct. So that's another, like the optimization maybe it can be performed is that we limit you can also set the settings in SVF. It's like we can limit the field number we try to analyze. So we just merge some of the fields. So to perform this analysis, we can lose some precision, but we have the efficiency. So for the C++, definitely they have lots of different features, especially for the call graph, the virtual calls. You have to figure out the call graph more precisely. Not only the class hierarchy, but also you have to try to figure out the points to information at the indirect call set. So we can try to analyze the the features call graph in C++ more precisely. Also the vectors in C++, I think is also important in the future work. Right?
Yes, thanks very much. It's very good too.
Yeah.
Thanks, Rick. Very nice talk. I have a practical question. So, are you doing any sort of modular analysis? No, you're doing monolithic, right? You're loading the whole program into memory, or you're kind of analyzing a module, getting some comprehension or some summary, and then going to other modules.
Yeah. Okay. I think it's a good question. So. Some of the thing is, if you load all the program into the memory and then try to construct all this, do this all sort of construction process, it takes long time and a huge memory, right? So I think one good direction is also, I think, is basically break down the program. Or maybe we can do some offline analysis and do some online analysis, and eventually we generate a graph, but during the process, like for each probably module or component, we can perform it offline and generate information, like dump them into like a file or whatever.
So you can do that if it's compositional, but if it's not, then you can analyze a module, then analyze another module, and then go back to the previous one and basically compute a fixed point over all the modules, like you're doing in memory, but you can do it piecewise.
So currently we are not supporting this, but I think it's also a good way. It's like you said, we can try to partition the program, so we can analyze some parts program and then generate information to a fixed point, and then try to combine them together later, right? Yeah, it's good.
Let's thank again our speaker.
Thank you.